Hello and welcome to the C programming lecture on arrays. What are arrays? Arrays in C give the programmer the ability to create a list, or in other words, an array of a particular type. Previously, when we needed multiple types, we would create multiple variables of that type. However, this can become a very cumbersome process. An array allows us to set aside a segment of contiguous memory of a defined length for a particular type. Each of the individual items inside an array is usually referred to as an element, and typically another word that is associated with arrays is the index, which is the value that we assign an element for actual access inside of the array. So here's the syntax of an array. It's fairly simple. We have a type, a variable name, some brackets, and some defined size integer. So here is a abstract definition. This is what one may look like with just the type, variable name, and defined size. Here's the abstract element assignment. The index here would be 0. So arrays are 0 base index. So if you have an array of size 5, your indexes start at 0. So it's 0, 1, 2, 3, 4. Those are the slots that you have available. So here's a concrete declaration example. We create an array of integers of size 10, and then we assign the first element to the value 5. All right, so here is an example of a program that creates two arrays. Our first array here is x, and x has the size 10. We manually assign the value 1 to the first element, and now here is our second array, which is y, also of size 10, and we just use this notation here to initialize all values within the array to 0. Now, depending on the compiler and depending on how you're compiling your program with particular flags or your platform, this may or may not work. So just keep in mind that this is something specific to a particular compiler as well. So you can see in our output, we're outputting the first element of x, which should be the value 1. And we're also outputting the fifth element of y, which should be 0 since we initialize every element inside of y to 0. And we can see this in our output, it's 1, 0. All right, so I want you to go ahead and pause the video and try this exercise. Write a program that declares an array of integers of size 5. Initialize each of those elements of the array to a particular value of your picking, and create a loop that will iterate from the index range, so 0 to 5. And you want to print out each value within the loop. So go ahead and pause it and come back when you're done. Okay, great. So here is my example of the exercise that we just did. So I have x, which is an array of 5, of size 5. And I have 5 elements here, just 10, 20, 30, 40, 50. And I'm going to loop over using a for loop. And I'm going to just print out every single element inside of here. And you can see the access for that is x. And then we have our brackets here. Within that is I, because this is being used for index. And that's pretty much it. That's all I did. Hopefully your program looks slightly similar. Obviously, some of the values may be different, and some of the ways you initialize the values may have been different as well. All right, so one thing I want to talk about is something called an out of bounds error. So what would happen if you were using a particular array and it was of size 5, and for some reason you accessed or attempted to access the 6th element? Now, this behavior that you are trying to produce isn't very well defined. So you're stepping over the bounds of an array in order to access some undefined memory location and maybe assign some type of value that doesn't associate very well with another variable. So stepping outside of the index range of a particular array is considered out of bounds. So what I just discussed and what I just described was a out of bounds error. So I go 1 over the actual size. So typically these are referred to as buffer overflows. So the opposite is when you go before. So if you go some negative index, that's typically called an underflow. So depending on what operating system defines a valid or invalid operation will determine if this program actually crashes during a read or write of a out of bounds index on an array. So I want to show you an example of this out of bounds read. So for instance, we have an array. We have two variables. You have an x, which is an array of 5 length. We have our 10, 20, 30, 40, 50 values inside of all slots. And then immediately after that, we have a y variable, which is assigned the value 1500 or 1500. So now what I'm going to do is I'm going to print out the last element inside of x, and then I'm going to go 1 element over. So that's 5. You can see that it prints out some number, some value here. Then I'm going to go again to element 6, which again goes to the next out of bounds element. So we are now 2 out of bounds elements. So some data that lives here, this happens to be 0. And then at our 7th element, it actually turns out that y is stored what it seems to be. So if we have an integer and this integer is a 32-bit integer, so it's 4 bytes, it appears to be, so this would be 8 bytes away from the tail end of our array. So we can actually access it by using a out of bounds index. So this is kind of an obscure thing. If you don't understand it at first, it's fine. But this is a exploitation inside of C code that you can use. You shouldn't use, but it can be done. So just like there's an out of bounds read, you can actually do an out of bounds write. So going along with what we just learned in the last slide, we have a x value here, our variable, which is 5 length, and then our y variable. So recall from the last slide that we recalled that the index 7 is associated with our y variable. So what we can do is we can print out this variable. See that I'm printing out y. We can then reassign a value of -1 to it and then reprint out the variable y, and we see that this variable has actually been changed. So this is the example of an out of bounds write. So this is why using an array in this manner is kind of dangerous. So another part of arrays is multiple dimensions of arrays. So like multidimensional arrays are being able to, we'll just stick to 2D for this particular visualization, but being able to declare basically a grid. So how do we declare that? How does it look like? So another way of thinking about multidimensional arrays is that you're just adding another indexable layer on top of the prior dimension. So this for 2D, it's easy to visualize because it's basically just the Cartesian coordinate system. So each dimension contains its own length when declared as well. So here's an example of a 2-dimensional array. And I said this would probably be the easiest to visualize, just because of then natural properties of you probably learning some type of mathematics that's similar to this in school. So to give an example of this, think of a table layout for a 2-dimensional array where the first index is the row and the second index is the column. So the indexes, again, go in order of the first index row and then the second index column. And we can see that in this table, I've kind of set up a way for you to be able to fastly kind of read that. So you can see all of the first brackets inside of this row all contain 0, and then in this column they all contain 0. Okay, so here is an example of how to declare a two-dimensional array. So you can see that I have a 3, so 3 by 5, right? So thinking about what that means, we have 3 rows by 5 columns. And you can see that I can organize it in a way which kind of makes sense. Obviously, these are not lined up, but you can see that there's 3 rows of data, and then 1, 2, 3, 4, 5 columns. Here is the for loop, and I just kind of print these out. You can see that I start with the rows and then go through each column. So it prints out, it should print out like this, go through each row and then go to each column. So 1, 2, 3, 4, 5, next one, and then so on and so forth. Play around with this code, definitely type this out yourself and just get kind of comfortable. You can even do a 3-dimensional array and see what that means and how to use it. So on the same note, multi-dimensional arrays are actually an illusion. So it's just a convenient way for us to declare a larger size one-dimensional array, because memory is linear, meaning that memory is just a contiguous block of elements. So the way that we index them by using these notations is easy for us to conceptualize, but the reality is we are just hopping row by row every time we go up by 1 inside this row major. So just to give you an example of what this would possibly look like, let's use the easy example of our 2D array. So we have here a 2 row by 4 column. Okay. So this is possibly what this would look like. We would have, our 0, 0 element would be indexed by 0. This next column, our 0, 1 column, would just be index 1, and so on so forth. So like 1, 2, 3, and you can kind of see that we have the ability to index every single one of these as necessary by just using a one-dimensional array. So to show you how this works, I have to introduce the concept of pointers briefly. Now, I don't think that we've covered pointers, and you've seen some of the syntax before. Now, you don't need to understand this because we will go into it, but this is basically showing you that I do not need the particular syntax up here in order to actually index into our two-dimensional array. However, that being said, at the end of the day, the actual indexing of this variable using the syntax is doing this underneath, or some form of this. Now, I'm not going to fully describe it because it probably will confuse you, but basically you can see here in this line, I'm printing out all the values just like the prior slide, but instead of using the actual index syntax, I have this obscure notation. Definitely try copying this down and messing around with it and seeing which results that you can come out with. All right, so an array recap. So again, an array is just a list that can be multidimensional, but they need to have a fixed size declared, typically defined by a constant integer. Array dimensionality is conceptual because the memory layout is linear. Therefore, everything can be expressed as a one-dimensional array. The convenient syntax of using the multiple brackets to have multiple dimensional indexes is, again, just for convenience, so that way you don't have to do this arithmetic with pointers. Again, we haven't covered that, but like there is some cumbersomeness to doing pointer arithmetic. So an out of bounds issue or a under bounds issue is an error that can occur when attempting to access an array index that is either smaller or larger than the boundaries of an array. Again, these are typically known as buffer overflows or buffer underflows. So let's go ahead and hop into some code and just play around with some of this stuff. Okay, let's go ahead and just hop into some code here and just mess around with some array structures and see. So first things first, I'm going to do my typical setup that I do, my hello world program. So I'm going to go ahead and just open up this file, do our basic stuff here. So nothing should seem too out of the unordinary at this point because we've done this a couple times now. So compile, run, hello world. Okay, great. So now we have our boilerplate stuff set up. We can go ahead and delete this. And let's go and continue with X. Let's say that we have an array of 10 elements. We can make an int, or better yet, let's do chars. So let's go ahead and say, let's just make a char array and just have, let's make it a little bit smaller. Let's just do 3. So we'll have 3 letters. Let's just make them A, B, and maybe like C, something along those lines. Okay, so here's our actual array. And what we can do is we can actually print out the array here. Let's go ahead and do a %C. Let's loop over this. So typically I'll actually make a length macro, and what's going to happen is what I do in this macro is I use the size of operator, and I'm going to pass in the actual variable, and that will give me the size of the actual array, and I'm going to actually divide it by the size of one element. So you may be asking what this does, and won't this break for other particular things? And the answer is yes to the latter, and the former I'll actually just show you. So let's delete this real quick, and let's just print out the length of X, right? So length, and recall that this length, this size of operator, what it returns. So the size of operator should return the length of bytes. So how large is one char? So it should be 1 byte. So this should return 3. So let's see what it says. Let's go ahead and compile this. But before we do, let's add a new line. Compile this guy. And it says 3, right? Because we have 3 elements and they're each 1 byte long. So now what does it mean when I index 1? So what it means basically is I'm doing something like the length of a particular character. So recall that one particular character is going to be 1 byte. So therefore this output should be 1. And that indeed it is. So we see that because this is essentially a character type and it's a character element, it knows that this length of this particular type should be 1 byte. So anyways, this is why I use this particular syntax for arrays. Now keep in mind that this only works with arrays that we declare within this stack scope, right? So if I pass this to another function, this would not work. So typically that's why you'll see functions and see that actually require a length, which we'll get into later when we start looking into the standard C library. Okay, so I'll just leave this here for reference, so that way you understand what this macro does, because it should tell you. So in this particular case, it's not incredibly useful, but if we were using ints or something that had a multiple byte structure, this would compute to the actual length that we could use. So what I can do is something like int equals 0 while I is less than the length of X. I want to increment I and then print out each character. So %C, and let's just do this with our x equals I. And there we go. So let's go ahead and declare another array. I'm probably not going to do any two-dimensional array stuff, just because I want to keep it pretty simple, not complicated or anything. And two-dimensionality, there's no really practical use right now in our study for it. So let's make it an int, and what we can do is let's just not even assign it any values, right? So we're just doing this. So now what we're gonna do is let's actually grab this guy, these two, print this same stuff out. Let's change these variables to y. And what we should see here, and let's go with so each one should be 4 bytes. All right, so let's do, so 4 would be 16. So we should have 16 length. Let's again, let's reuse the I. Sometimes you'll see I, sometimes people will use IDX. It's just, it really doesn't matter. Just showing you typical things that people may use. Printf, and what we're gonna do is we're gonna print the value of y here, just like we did up here. So let's add a C. Let's add an X actually. X. And let's do index. So I here, so it will be %d. So I just want, this is really just for clarity of what we're indexing. So we have I, so that should make sense. But this needs a semicolon. Okay, great, perfect, exactly what I wanted. Let's go ahead and add a new line and rerun this. Okay, perfect. All right, so let's do I. Yeah, okay. So what is happening? So we just cleaned up some of this this output to show exactly what we're outputting and what the variable is. So the variable with the index plus the actual value. So I misspelled length here, just realizing that. And let's just recompile. Okay, so, but another question before we get into this output and why this stuff looks crazy, let's go ahead and just review this real quick. So we have when we do the length of y, just like I said previously, it should be 16. The reason for that is because a integer in this particular case is 32 bits or 4 bytes, and our size of operator returns the amount of bytes. Since there's 4 of them, since we have 4 elements, it'll be 4 times 4, which is 16, and then we have a individual element, which I just said previously. Since this is an integer, it's 4 bytes. So basically, when you think about this, when we expand this out, our macro, it goes 16 divided by 4, and what is that? Well, that happens to be 4. So this length operator, or this length macro here, is nothing more than replaced with this equation, which just boils down to the constant value 4. So, but why is it outputting this craziness here? Well, that's because we declared a array with uninitialized variables. So for instance, if I went in here and I assigned this to equal, let's just say 100, we should now see our first element equal to 100, but the rest is all mangled up. The reason for that is because depending on how your compiler works or what it guarantees, these may not be initialized. So recall from the slides, what I had to do was possibly something like this in order to guarantee that the compiler will clear out all variable values, all index values inside of our array to zeros. So you can see again, if I remove this, this will be garbage. But if I added it, it won't. And just for clarity, let's go ahead and do that exact thing in here, and we'll make Z. So same exact deal, except we're actually going to skip over printing this stuff out, and we're just going to grab this guy and we'll initialize him to 0. Sometimes some syntax is weird and it may allow this, although I don't think this is going to, oh, it does. Okay, so this may actually zero out as well. But that's pretty obscure syntax. We'll see in 1 second. So this needs to be Z. This needs to be Z as well. Okay. Yeah, so this appears to work. I know in the past, like some compilers only support this rather than this. So eventually in the future, we're going to have another series that is with MSVC, and so that's Microsoft Visual C compiler, and you will notice substantial differences between GCC if you take this course with the other course that I'll be creating, which is using basically Win32, the Windows platform for C development. You're going to know substantial differences, just like the one I showed you, what's allowed and what's not allowed. And this just boils down to the fact that the C spec on both of the compilers is just kind of in a weird mangled state for like there's a standard, but not everybody technically follows it to a T. So anyways, so I hope this brought some insight into some array syntax and also concepts. Again, just so that we're clear, this last concept, when you do not initialize, so like not adding these braces here, these curly braces, it's not the compiler GCC that we're currently using is not going to guarantee that it clears out any memory. However, when you add it here, it's going to zero your memory block out. Even we can see that here, but because we are actually looping over this entire array of Z and outputting each of these individual elements, and they're all 0. Anyways, thanks for joining me. I hope to see you in the next lecture.